up because in order to go from one side to the other, you should have taken one side only. This is now our given. This is now our prove. We're not allowed to use our prove. We're supposed to arrive at our prove. So therefore, multiply this guy by sine over sine. Multiply this guy by cosine over cosine. What identity would you guys have needed to know to be able to finish this puppy off? Because common denominators is just like math, right? To put fractions together, common denominators, it's just like math. But right here, when you get sine squared theta plus cosine squared theta with the common denominator of sine theta cosine theta, what identity did you have to use? Pythagorean, yeah. What's sine squared plus cosine squared? Sine squared of theta plus cosine squared of theta. Ah, and why was that a good thing?
Because now you can split up cosine.
Mathematically, yeah, you are allowed to make this 1 over sine times 1 over cosine. Fractions, I can't add or subtract fractions unless they have common denominators, but I can multiply, divide fractions just by taking them apart. Because multiplication, tops multiply, bottoms multiply, totally legal. And now if you, well, hold on, what properties tell us that this is cosecant of theta and this is secant of theta? Not Pythagorean, not inverse. Inverse goes backwards, right? This isn't backwards, this is upside down. What's the mathematical term? Reciprocal. There you go. There you go. Have we arrived at our proof? Yes, we have. Dun, 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 dun. With common denominators, with Pythagorean, with reciprocal. Okay.
Basically, you just have to go backwards if you start with the right side, right?
Just you shouldn't show that work. And if you do, put it on a separate piece of paper. But yeah, you could always off to the side be like, hey, he's 1 over sine. Hey, he's 1 over cosine. Then you could have compared the two and said, oh, hey, got it, done. But you just can't put it in the same proof as far as properly going from the given to the proved to show the progression. You want to go one direction only. Now, here's only not that kind. The other polygon, but it's only for the very, not the faint of heart, and the very creative. You could have gone cosecant as 1 over sine, secant is 1 over cosine, both of thetas. And then you could have said, I bet 1 should be made into sine squared plus cosine squared. It'd be quite the jump, but some of you maybe could have done that. And then you could have split up this guy over plus that guy over and then simplified and simplified. You could have technically gone backwards. It just would have been a lot harder. Because going from here to here, 1 can be all sorts of things. That's not the only thing that 1 can be. So maybe just a few of you could have gone backwards, but most of us, the easiest way to go would have been forwards, which is why we went from the left to the right. That's not always the case, though. Sometimes it's easier to go backwards from the right to the left. And sometimes both of them are hard, and like Kyle said, you kind of go off to the side and say, what's going on that side that I can maybe somehow go partway here and partway there, meet in the middle, and then take those steps and finish off to make my full proof. All right, cool kids. With that, let's go ahead and grade section 4.3. How was this compared to the ones in homework? Harder, easier, the same? Oh, okay. Okay, it's not that much different. Let me close the door because it's kind of chilly in here now. And we're looking at homework number 25. Zoop. Section 4.3. And you guys were using triangles, true? Let me zoom in a little bit because some of these fractions get small. All right, number 12, there's a lot to check. Let me give you a little bit of time. Number 12, there's a lot to check. You can do it. Put a little power to it. Oh. What was the step that was, well, hold on. First of all, the very first thing you had to do was solve for who? The hypotenuse using what theorem? So first step, Pythagorean theorem. Then you have your opposite, your hypotenuse, your adjacent. All you need is SOHCAHTOA CHOSHIKAO. But this doesn't look like, oh, what happened in between here and here for both of these? What's the step that lets you go from opposite over hypotenuse to root 5 over 5? Proper simplification should not leave a square root in the denominator, so how do you go from here to here? Okay, hold on. CHOSHIKAO is all of these way over here. SOHCAHTOA is these. But what I said is once you have your opposite over hypotenuse, how do you go to this form? What'd they do? Kind of. Multiply top and bottom by root 5. The conjugate has the plus and minus switching, so it's not the conjugate. The word you're looking for is the process of rationalizing. Rationalizing the denominator. Making the denominator into a rational number. Because if you say, hey, it's 1 square root of fifths, like who knows what a square root of fifth is? I don't know. But square root of 5 over 5, oh, hey, it's cut into fifths, and then we have 2 point something something of those fifths. This one is a lot easier for our brains to make sense of if the denominator is a rational number, thinking of fractions and cutting into pieces. That one, I don't know what to do. 1 over 2-ish, it gets a little hard, but fifths, and then you have 2-ish of those, a little bit easier. Anyway, rationalize the denominator. What was weird? What ended up happening? If you did it right. They're the same. Why are they the same? Because they're similar triangles, and similar triangles have proportional sides. So even though this one is 1 and 2, the size of this triangle is smaller. Its trigonometry, its trigonometric ratios will be the exact same. Because trigonometric ratios are not dependent on size, they're dependent on ratio. So whether you have a smaller triangle or a bigger triangle, if their sides are proportional, their trig should be the exact same, which is why we're able to take, what was that? The 30, 60, 90 and the 45, 45s, remember from Friday? It's why we were able to take a bigger triangle from geometry and apply it to the smaller, similar triangle in the unit circle. Some of you guys are just going to use this point, the x and the y, to find all 6 of your trig ratios. Some of you guys are like, give me a triangle. I want to do SOHCAHTOA CHOSH cow all day long. They'll end up being the exact same thing because of this property of similar triangles. Okay, number 24 and 38. Quick conversion. A quick conversion just to realize it was a 30, 60, 90. You could plug in your ratios and then you end up opposite over adjacent for tangent. Or some of you, to be honest, might have just used the xy from the unit circle and you kind of cheated and said, haha, I know what it is also. Number 38, you were plugging and chugging to your calculator. How did they plug and chug? Can anybody find the typo in letter A? There's a quick little typo. Where is it? The answer's right, but where's the typo? Says equals. That doesn't make sense. It's 56 degrees, 8 minutes, 8/60th of a degree, and 10 seconds, 3600th of a degree. That should have been a plus. Yeah, that should be a plus. But wait a minute. Doesn't your calculator do degrees and minutes and seconds? Did you have to do this? No. Dun, dun, dun. Wait, how do you do secant in your calculator again? 1 divided by, you have to use the reciprocal property. 1 divided by cosine of. And then that was just a plug and chug, right? 54. That was a quick, they chose, was that the left side that they played with? I think they played with the left side. And they changed cosine squared to be 1 minus sine squared, then a quick little distribution. The sine squares end up combining, and dun, 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 check. Then number 70 was a word problem, where ultimately you wanted to know the adjacent, you did know the, you wanted to know the opposite, you did know the adjacent, they gave you the angle measure. All you had to do was plug into degree mode and label it with feet. With that, I'm pretty sure we're at the end of our evens. Not the end of our ropes, though, hopefully. My question to you is the following. Any odds or evens that we need to look at in more detail? I'm ready and a raring to go. I had part of my coffee this morning. 87D. Anything before 87? Going once? Going twice? Sold. Remember, you guys should... There he is. Hey, what should your calculator be in for number 87? Degree all the way, right? All the way. So as I'm getting at my calculator, let's go ahead and see what the question is asking. There are no other directions earlier, I don't think, as far as for that particular question, so it's all self-contained. Think about it. Complete the table. All right, I can plug stuff in. Behavior. Uh-oh. Oh, come back. Wait for it. Okay, discuss the behavior of the sine function for theta in between or in the range. I know, I need to put my site license in. 0 to 90 sine function. Use the definitions of sine and cosine to explain the results of. Whoa. Okay. I'm going to go ahead, and since we're just looking between 0 and 90, is it okay if I have you guys visualizing this part of the unit circle? Is that okay? Okay, all the angles 0 to 90. 0, 30, 45, 60. Well, they did some weird ones. 18, 36, 54. Did you guys figure out a pattern just so we could do this simpler, quicker in our calculator? What's the pattern of those values if we have to go to our table anyway? By 18s. Good. So I'm going to go ahead and, well, you guys help me out. You were doing this. I'm going to put in my sine. I'm going to put in my cosine. There is no theta in this mode, so I'm just going to use x. No big dealio. It's a variable. If I go to my table right now, is it going to be perfect and ready? And first of all, delete all that stuff. That's from who knows a long time ago. But how do I make the table do what I want it to do? Second. Oh, come on. We know how to mess with our table, don't we? How do we mess with the table? Yeah, second what? Window. There you go. Start at 0. No big deal. Go by, no, not ones. Let's go by 18s, huh? And then, why am I not going to keep it on ask, but I'm going to auto? I want it to. Yeah. It'll land exactly where I want it to go. So therefore, that should have been all that stuff. That should have been, I'm just going to leave it up over here to the side. That should have been all of your values for, wait. Am I in degree mode? Ooh, that could have been a mess, huh? If you were in radians, you're going to get very different answers because radians measure very differently than degrees. Okay, there we go. I have 0 to 90, 108 I don't care about because they didn't ask for that. They asked me to stop at 90. How'd you guys answer for letter B? Yeah, Gavin. Good. Between 0 and 90, sine will increase as theta increases up to its maximum value of 1. Wait, how do I know a sine can't go beyond 1? True, and it does start to go back down, but just because of the circle, how do I know that sine can't be bigger than 1? Sine is the y, right? How tall can the y be? What's the maximum height of the unit circle? 1. And what's the lowest height? -1. So I know sine has to be in between 1 and -1, because y's can only go up to 1, down to -1. That's it. So sine increases highest 1. What does cosine do? Decreases from 1 to 0. So sine increases from 0 to 1. Cosine decreases from 1 to 0. And then it says in letter D, and this is, I think, your question, right, Kim? Your definition of the sine and cosine functions to explain the results. I'm going to go over here, and I'm going to show you guys a few things. What if I was to show... Okay? Going from 0 to 90. Isn't that kind of what the table does? Yeah. It starts at 0, up a few, and then goes in 90. As we do that, what if I was to draw the little triangles for each one? I mean, this one's like a flat triangle. That's kind of lame. But then it goes, and then it goes, and then finally goes, right? So it starts at, the point starts at 1, 0. It ends at 0, 1. As I look through this, and we can put lots of points. We could have lots of triangles and make a little animation about it if you're good at computer programming. And we could show how the triangle's going up and then getting narrower as you go down, getting wider and wider until it's a straight line, horizontal, vertical. Which one goes with our x's again, guys? Cosine, good. So, Kim, you have two options. One is to use the cosine of theta is equal to x, and we're talking about the point xy on the unit circle. We could use that definition. Or we could use cosine of theta equals adjacent over hypotenuse. And check out what's going on. If the cosine is x, what's going to happen as we rotate from 0 to 90 to the x's? What's going to keep on x's? They're going to decrease until they hit 0. That's exactly what the table showed. And what's going to happen as the y's, or to the y's, as you rotate around the unit circle? Well, the y's are going to increase. So since cosine is x and sine is y, as you rotate from 0 to 90, the x's will decrease and the y's will increase as the table showed. The other way of explaining it, using the triangles, both ways are good. Using the triangles, what's growing as my point goes to 90? The opposite or the adjacent side? The opposite side is growing as what's shrinking? The adjacent. So instead of using y and x, you could also use opposite and adjacent and say the opposite side is growing as the adjacent side is shrinking, so therefore sine, which is built on opposite, will be growing or increasing. Cosine, which is built on the adjacent, is going to be decreasing. They both depend on the hypotenuse, so it doesn't really matter as far as they both are being affected by the hypotenuse the exact same way. What's different is the adjacent and the opposite. Adjacent shrinks, opposite grows. Okay? Any other questions after 87, or was that the last one? Okay. So let's go ahead and put away this homework. I want you guys to grab out your notes for section 4.4. I did have a question on the calendar, so I'm going to go ahead and pull that up really quickly so we can peek at it. Oh, except I guess I'm signed out. That's weird. I wasn't signed out a second ago. Now I'm signed out. Let me get you guys back into notes so you can start on. We haven't started 4.4 yet, right? Oh, hey, I had 87 ready to go in the notes. I just forgot. Oh, well, we already covered it. You guys were okay on the Empire State Building, huh? Okay. Section 4.4. Some of you guys might have noticed on the calendar that there is seemingly a quiz coming. The answer is yes, but the answer is also not tomorrow. The answer is yes, a quiz is coming, but the answer is also not tomorrow. Let me freeze the screen so that you guys can get that. Let me pull up the calendar. Shoop, shoop. So that as you have the notes ready to go, I can have our schedule ready to review for you. Talking about our unit circle, because we've been talking about how to do it. I haven't been forcing you guys to get good at it or to master it per se. So today we're going to actually finish off the final way of looking at the unit circle, or at least the final information regarding it. There is going to be a quiz on Wednesday. We'll look at that calendar in just a second. But first of all, let's go ahead and figure out what's going on in section 4.4. So what quadrant is the point? Negative 3, 4. So I can go left 3, up 1, 2, 3, 4 approximately. With the point negative 3, 4. What's the sine, cosine, tangent? You have to make a triangle. I think that's at least the easiest way, right? Of going up 4 and going left negative 3. True? Now, technically, there is an angle inside the triangle. That's true. But as far as theta and what theta is going to be the other angle that rotates to get to that triangle. Because I need theta to be a second degree angle. That way it makes sense. If I use this little, like, for instance, what if this was something like negative 3/4 would be closer to 1 than 1/2? 1/2. So something in between pi over 4 and pi over 6, which would be something in between 135 and 150. Let's say this was something like 147. It's not, but let's pretend this was 147. We could use the little baby angle. Wait a minute. If this was, for instance, if this was the angle 147, which it's not, I'm not promising it is, what would be the little angle inside the triangle? How could you do that math? 180 minus 47, so it'd be 33 degrees, right? But if I was to say what's sine of 33 degrees and cosine of 33 and tangent of 33 degrees, I would get the right numbers, but I wouldn't get the right signs because 33 degrees actually should be in the first quadrant, right? So I need the big old 147. I can look at the triangle that it hits, for its values, the 3 to the left negative and the 4 up positive, but I shouldn't be using the 33 if I was, like, for instance, using my calculator. I should be using the one old big 147. So that's all to say this is why this angle is theta. This angle is useful. The numbers would be right, but the signs would be wrong. This angle is important because that says second quadrant, oh, the x is negative, y is positive. And as you guys go to plug in, did most of you guys just think SOHCAHTOA? Did anybody think x, y? Oh, okay. But for the rest of us, SOHCAHTOA, if you can make the triangle, wait. Sine needs a hypotenuse. Oh, it is 5. Technically, if you guys want to think about it, the unit circle would actually be way down here because the unit circle would just go down one. But that's okay. I don't care that the triangle is outside the unit circle. I could scale it back, similar triangles, or I could say forget it. Just find his ratios. It doesn't matter. The ratios will be the same. So what's the ratio of opposite over hypotenuse? Got it. And it's positive because the y is positive, right? Or all students. Sine is positive. Cosine. Adjacent over hypotenuse, or negative 3 over 5. It's good that it's negative because the x is negative in the second quadrant. All students. Sine is positive, not cosine. Or just look at the triangle. Don't you have to go left 3? Tangent. 4 over negative 3, but guess what? If you were to plug this in your calculator, it would just say negative 0.75, which looks like negative 4/3. Sorry, not 0.75. I apologize. 1.3333. So even though you could write it like this with a negative down in the denominator, if you were to do it in your calculator, it says a positive divided by a negative is a negative. It's going to look the exact same as that one. Now, could you do HPrecalc? Yeah, what would cosecant be? Good. What would secant be? Negative 5/3. And what would cotangent be? Negative 3/4. So we could do HPrecalc, but they didn't ask for it. So if they give you a point, now this one's kind of hard, but graph the point and then make a triangle, and you're good, you're golden, you're ready to go. So we need to talk about something called a reference angle. We've done in the unit circle angles that were bigger than 90. We did, but we didn't go into the detail or the vocabulary as far as the pieces for an angle bigger than 90. This one right here is kind of like what we just saw. There's a theta that lands or has a terminal side in the second quadrant. But to make the triangle, to do trigonometry with a triangle, we'd have to look at this extra little guy. Or I should say, make a triangle out of that extra little guy. That extra little guy we actually have a name for, and his name is the reference angle. So for instance, we could actually say, hey, reference angle, and we're going to label all the reference angles in this page of notes. The book could do differently, but I'm going to label him as alpha. I'm going to label him as alpha. So we have our theta that's starting in standard position and rotating to land at a certain spot. The reference angle is going to be alpha. The words of the description for the reference angle would be an acute angle between the terminal side, where an angle ends, and the axis of the initial side, aka the x-axis. Or for standard form, the x-axis. Every now and then we measure differently, like if you're doing a north, south, east, west problem. Sometimes they measure from north because of like the origin of navigation. The North Star was what they measured from. So sometimes with bearings, compass bearings is what we call them, we would start from somewhere else. But for us, for right now, standard position is always starting here, which is like due east, always starting there and rotating. The reference angle is what's left over to the horizontal. So what's left over? Well, there's what's left over. Here's our theta. Alpha would be this little baby guy in the third quadrant, right? That's what's left over. And then here, theta is going all the way around the fourth quadrant, and alpha would be this little guy. Bless you. So my question is, what's the math to find alpha in this case, to find alpha in this case, and to find alpha in this case? Yeah?
Isn't the reference angle wrong for the middle one? Isn't it the other way? Because that angle's going in.
It doesn't matter. Because what matters is that I need to have it, the angle, the terminal side where the angle ends, and the axis of the initial side, aka the horizontal. So you would have gone to the vertical, and that's the wrong angle. But that's what a lot of kids would have done on accident. So if you notice, the first and second examples, case 1 and case 3, it's like, hey, what's left over? Not what's left over, I should say. What's extra? How much more to get or to finish? The first one, how much more to finish 180? Or how much more to finish pi? How much more to finish the whole half circle? The third one is how much more to finish the whole circle? How much more to finish pi? How much more to finish 360? The second one is very different, though. The second one says how much passed. So the questions are a little different, but the reference angle, the idea is still the same. What math would you guys, or did you guys just do, Adam did it a second ago for the last example, to find alpha? 180. Or if I'm trying to get you guys to think in radians. So if you have an angle in the second quadrant, to find the reference angle, you can always do 180 minus theta or pi minus theta. It depends on whether you have degrees or radians. Now what would be the math for number 2? Yeah. Well, too, this one's a little trickier because you could say alpha minus 180. Wait, but we're trying to find alpha, aren't we?
Theta minus 180.
There you go. Alpha is equal to theta minus 180. Or theta minus pi. Question though. If we did something like, maybe I shouldn't do an example right away, but I kind of want to. What if I was to give you one of these? Because case 2 is kind of one of the hard ones. Let's do a quick case 2 example. What if I was to want you to find the reference angle alpha for theta equals 4 pi over 3. Would he be 1 to the pi line or to the 360 to the 2 pi line? Because we're either going to this guy or going to that guy. If we have to go to the horizontal axis, either him or him. So where is he? Is he less than 1.5 or is he more than 1.5? That's the real question. Does he dip into the 4th or is he still in the 3rd? He's still in the 3rd because how many count? 3 slices and 1 more, right? 1 1/3. So who's his closest axis? Pi or 180. I'm doing pi because I have radians. Could I, question, reference angle, could I still do, pi is the closest, could I do pi minus 4 pi over 3? I would get -1, right? Because I have 3 over 3 and I subtract 4 over 3. I would get -1 over 3. But here's the problem. All reference say, hey, if it's smaller, if the angle is smaller, then do 180 minus or pi minus. If the angle is bigger, do the angle minus 180, the angle minus pi. What mathematical symbol could we actually put in to make this so you only have to remember 1? Positive or negative? I want it to be positive. What math makes positives or negatives always positive?
Absolute value.
Absolute value. So what we could do is say, hey, alpha is always just the absolute value of subtracting to the closest horizontal axis. You can always do the closest horizontal axis minus the number or minus the angle that you've been given. So if it's in the 3rd quadrant or 2nd quadrant, you can always do pi minus 180 minus, but you could just think of absolute values if you want, if that helps. Or if you don't mind finding which one and then switching around the subtraction if you need to, taking the bigger minus the smaller, that's okay too. Both ways work. But just showing you guys you can just put in absolute values also because reference angles are defined to be, maybe we should mark this. Reference angles are always positive. Reference angles are always positive. They need to always be positive. They're defined to be a positive angle. So reference angles should never be negative. We're just trying to figure out what that little extra rotation is, regardless of direction, regardless of where it is. Just what that measure is, aka the absolute value, aka the always positive. Okay. Beep, beep, beep. Oh, we didn't do the last one. Guys, what's the math to fill in this last one? Good. 360 minus theta, or 2 pi minus theta. And if you did theta minus 360 or theta minus 2 pi, you'd be okay also as long as you put in absolute values. Because the way it is now, 360 is the bigger number, 2 pi is the bigger number, so if I subtract it this way, I end up with the positive that I need. Okay. What else do we have? Set up a triangle with the reference angle. If we're trying to solve for trig functions, first thing we want to do is figure out what is the reference angle. Second of all, try to fill in the information for the triangle. And some of you guys very naturally were like, oh, -3, 4, yeah, it's a triangle, no big deal. That's cool. That's going to be helpful. But if you have an xy, that's what we just saw. If you have an xy, you can go ahead and right? You can go ahead and use the xy to solve for your triangle or to set up your triangle. They call their reference angle theta prime. That's kind of weird. I like alpha better, but whatever. Watch out for signs, because when you're using a reference angle, it does not include the sign. So I'm going to say all students take calculus. Quadrant 1, quadrant 2, quadrant. You just might want to make sure that you have the correct signs. Sometimes we go a little bit fast and we're not going to think about it. It's not as carefully as we should. And then solve for the appropriate trig functions. Well, I don't know what they're going to ask you, but whatever they're going to ask you, if you have a triangle, can't you always think SOHCAHTOA and CHOSHCAHTOA? Hopefully. You still have the unit circle XY formulas. If those are in your brain, you can be using them. But if you have your triangle all set up, you can also really quickly do SOHCAHTOA, CHOSHCAHTOA. Kyle.
So you can use the interval even if not one?
Because the ratios, when you're finding trig, when you're finding sine, cosine, tangent, cosecant, secant, cotangent, and because the ratios are going to be the exact same. Kim? No. No. But that means that the only angles I'm going to give you are degrees and or radians. I should say radians and or degrees, mostly radians, with either sine of, cosine of, tangent of, cosecant of, secant of, cotangent of, the nice ones that you could do from the unit circle or from the 30, 60, 90, 45, 45 triangles. Find the reference angle for each. Hey, what quadrant, guys? Fourth quadrant. So can't I just do 360 minus 300? So alpha is going to end up equaling 60 degrees. 2.3. There's no degrees, so what is it? Radians. If I was to take any circle, the radians, and measure 2 of them around, where would I end up? Second quadrant. Oh, so isn't this just going to be pi minus 2.3, which is leave it like that. It's in the second quadrant. Yeah, 3.1415. You could take some time, though, yeah? Negative 135. What quadrant is he in? 2.3 is here-ish, which is why I use the trick of 180 minus to get my alpha. This guy, 300, was here-ish, which is why I use my 360 minus to get alpha. And this one, negative 135, is what quadrant? Third, because I have to go negative, technically 3 pi over 4, so negative 3/4 of that calzone. I'm going to use, the answer is 45 degrees.
Oh.
But what's the math for it? 180 plus negative, yeah. 180 is the closest one. I have to just somehow subtract them. So the math kind of changes, but the idea is the same. You always just think of, hey, what's the closest horizontal? And it's either 180 or 360. It's either pi or it's 2 pi. And then somehow subtract, keep the positive answer. Don't make it negative. Does that kind of make sense? Those are for reference angles. Oh! How on earth can they just ask me this then? Well, it's kind of like the quiz on Wednesday. The quiz will just be with more questions. It is going to be timed. It is going to be timed. You're not going to be able to sit there forever. But guys, there are multiple ways of doing this. For instance, on letter A, couldn't we think about 1 1/3 calzones hitting in the third quadrant with a point on the circle of, left a little, down a lot, so that'd be -1/2 and -√3/2. Then we could say cosine is the x. Oh, hey, that's going to be -1/2. Or, couldn't we think of the reference angle? Think, oh, that's down here, which is going to end up being a 60-degree triangle. And a 60-degree triangle is going to end up having an opposite of -√3, an adjacent of -1, a hypotenuse of 2. And couldn't we say, so ca, adjacent over hypotenuse, is -1/2? So whether you use the circle point or whether you use the 60-degree reference triangle with the right signs because of the quadrant, left and down, they both work. Not the only way. We're going to play with these other ones, maybe homework's due tomorrow, but we're going to play with these ones maybe a little bit more tomorrow. This quiz isn't going to be until Wednesday because we're going to work a little bit making you guys fast. But there actually is something kind of cool that you could do in order to make this go a little bit faster. Because we talked about how sines or the opposites grow from 0 to 90 and cosines shrink or decrease. Sine starts at 0, ends at 1. And didn't we talk about the tricks of the fractions? Square root of 1/2, square root of 2/2, square root of 3/2, right? You grow up to 1. Cosine goes backwards. What does tangent do? Opposite over adjacent, sine over cosine, y over x. What's 0 divided by 1? 0. What's 1/2 divided by square root of 3/2? The 2's cancel. You just get 1/√3, which is the same thing as square root of 3/3. Divide those two, it's 1. Divide those two, it's √3. Divide those two, it's undefined. From some students from Brazil, Luca Kohlberg to be exact, from a couple years ago, 1, 2, 3, 3, 2, 1, all over 2, and square rooted. He didn't have that in his song. Square root of 3/3, 1 square root of 3. Ah! So many ways, 3 ways to be exact, a circle, triangles, and a cheater chart. You guys need to figure out how unit circle is going to make sense in your brain. Own it. Come tomorrow. We're going to try to make you fast. Bye, cool kids. Try to finish up 4 for tomorrow. Technically, we probably won't grade it until Wednesday. We're going to be working on our unit circle. Bye. It was left last week. Oh, is it? Go ahead and take it for you. Bye, Rachel.